Okay, so we're doing chapter 3 of scaling networks, and so it's spanning tree protocol, or STP. So what are we going to cover? So we're going to look at spanning tree concepts, and then we'll look at varieties of spanning tree protocols, because there's been a few different versions, some proprietary, some standards based, and also we'll look at how we configure a spanning tree. Okay, STP operation. So we talk about redundancy all the time when it comes to making things more reliable, and so layers 1 and 2 are no exception to that rule. And so switch networks commonly have redundant paths and even redundant links between the same two devices. Redundant paths eliminate a single point of failure in order to improve reliability and availability. So redundant paths can cause physical logical layer 2 loops. Now layer 2 doesn't have a so there's nothing in the headers to sort of allowed for this to happen, and so we need a layer 2 protocol called spanning tree protocol that helps, especially when there are redundant links. So if you have layer 2 loops, MAC address database can become unstable, and so because frames can actually start looping around endlessly, it can actually point to the wrong port to get to that destination MAC address, and so that can be bad. Broadcast storms are of course where someone sends a broadcast, and that happens pretty regularly, and so those frames, because there's a loop, will just continue carrying on, and so basically will chew up all of your bandwidth that's available, and yeah, no other traffic will be able to get through, so that's not good. And another one can be multiple frame transmission. So multiple copies of unicast frames can be delivered to the same destination, and so it's just wasting resources at the very minimum. Okay, so the issues. So Ethernet frames do not have a time to live field like a layer 3 header does. This means that Ethernet has no mechanism to drop frames that have been propagating endlessly. And so basically if PC1 sends a broadcast frame to switch 2, so switch 2's down here, PC1, every other device will see that frame. So switches by default send a broadcast out all other ports, and so these two hosts will see it and it will go to those two switches. So of course these switches will do exactly the same thing. It's come in here, and so it will go out that port and that port, and this one will send it on, and so on. And so as you can see, on trunk link 3, there's going to be the same broadcast going in opposite directions, and so it just, and there's no way for the switch to know that it's already seen that same frame or different copy of that frame already. And so basically it will just keep going and keep going and keep going. A host caught in a network loop is not accessible to other hosts. Due to constant changes in MAC address tables, switches S3 and S1 do not know which port to find the frame. So of course, we're talking about MAC database. When it goes that way, it's, oh, well, PC1's come from here, and this one will think PC1's come from here, and then we'll cross over. Oh, now PC1's come from here, and it just rewrites entries, and it just goes ballistic. And of course, this switch will see them again eventually too, and say, oh, okay, PC1's over there. Oh, wait a minute, no, PC1's over there, and so it will just be completely confused. So of course, broadcast storms is just frames everywhere, and so basically you'll end up with called, I suppose it's an accidental denial of service. It can develop in seconds and bring the network down. So I actually had one of them at my home. I had a center switch, and then I had an access point hanging off of it, which also had extra ports. I used to have just a spare cable hanging off the access point, so if someone wanted to hook into the Ethernet, they could and use it. I think it was one of my sons, saw the extra cable. Oh, that should go there, and so put 2 links between my little cheapy home switch and my access point, and yeah, I had a broadcast storm, and nothing was getting through. So apparently those little cheapies don't run spanning tree protocol. Anyway, So duplicate unicast frames, and so an unknown unicast frame is when the switch does not have the destination MAC address in its MAC address table. And so again, switches can do three things. They can forward, filter, and flood. And so basically, it's a flood. And so a flood is pretty much the same as a broadcast. And so the unknown unicast frame sent onto a loop network can result in duplicate frames arriving at the destination device. And so PC1 sends a frame to PC4, which is over here. And because this switch doesn't know where PC4 is yet, it mustn't have done any communication that it's seen. It will send it out the other ports. And so one will go that way and the other one will go that way. And they will both get to PC4. Now, spanning tree algorithm. And so the spanning tree protocol creates a one logical path through the switch network. And so all destinations on the network will be able to talk, but there will be no loops. And so it blocks redundant paths that could cause a loop. Spanning tree protocol sends bridging protocol data units, so BPDUs, between layer 2 devices in order to create one logical path. A port on S2 is blocked, so traffic can only flow one way between any two devices. When trunk 1 fails, the blocked port on S2 is unblocked and the traffic would then be able to get through to S2 and S3 again. So you still get your redundancy, but you also don't get those switching loops where traffic just goes bad. Now, to get it to work, you need to have different devices and ports having different roles. And so the first role is that you will have a root bridge. And so that root bridge will be the device that is deemed to be the center of the network or the starting point of the network. And then a root port is one port on a switch that has the lowest cost to reach the root bridge. Now, a root bridge will actually never have a root port, but all the other bridges will. And so in this case, this is the root bridge for switch 2 because that's the quickest way to switch 1, which is the root bridge. And here it has a root port because that is the quickest way. And so a designated port is selected on a per segment basis based on the cost to get back to the root bridge for either side of the link. And so as you can see here, the designated port here is active, and so away it'll roll. An alternate port with rapid spanning tree protocol is a backup port for the designated port when the other side is not a root port. And so the backup port is a backup port for the root port, basically. Now, how do we get a root bridge? And so basically, the bridge with the lowest priority will become the root bridge. Now, basically, the priority is a combination of the priority number plus the MAC address. Now, the priority by default, it's a 16-bit number, and so 65,536 is the number of numbers it can have, and so the default priority is halfway. So and so if no one configures the priority of a switch, they will have the same priority, but it will be the MAC address that will be the tiebreaker, because every switch will have a different MAC address. And so there will be a root bridge. Now, leaving it to the default to do that, you may end up with a non-ideal solution for it. And so you can actually change the bridge priority so that you can actually manipulate that. And so you would normally have your core switch to be the root bridge, because that's typically where most traffic will go. And so if you've got the other switches having the ideal path to that root switch, you'd think that traffic would move around the network more efficiently. And so basically on that core switch, you would then change the bridge priority to be lower than 32.768, and then that will normally mean that will become the root bridge, and paths will be optimal towards that root bridge. Now, The route path is the cost used to determine the role of the port and whether or not traffic is blocked. It can be modified by the spanning tree cost command on a per interface basis. And so from there, basically, you have a route bridge, and then of course the other bridges figure out their route port by the port with the lowest cost to get to the route bridge. And so if you don't manipulate the cost, it's just based on the bandwidth of the port. And so of course, the higher the bandwidth, the lower the cost, and so the more desirable it is as well. And so, as I said, you can change it to manipulate the, again, the way the spanning tree will come out. Now, port role decisions. So, you have the route bridge. And so a route port, of course, is the one with the lowest cost. And so you've just got one fast Ethernet link to get to the route bridge with those links for those switches. Of course, they could get to it that way, but you've got two fast Ethernet ports, and so that will be twice the cost, and so that would not be the way it goes. And so the route port, of course, is the closest way. And so, of course, you've got designated ports. Often you just look at the designated port. It will be on the opposite end of the link that the route bridge is on. That's how I normally think about it. Now, port role decisions for RSTP. Which port is going to be the designated port? Now, after S3 and S2 exchange BPDUs, STP determines that fast Ethernet 0/2 on port S2 becomes the designated port, and on switch 3, the port will become the alternate port, thus going into blocking state. So there's only one path through the switch network. And so that is all based on which bridge ID is the lower. Now, determine designated and alternate ports. Okay, we've got a different topology now. Remember, port states are based on the path cost back to the route bridge. And so, again, we've got the route bridge here is S1. So that'll be a route port. That'll be a route port. With this one, you know, it's probably going to be a toss-up. They're all fast Ethernets. But basically, the lower the port number will actually make it more likely. Okay, so we've mentioned BPDUs, and so basically here we've got the frame format, and we've actually also got I was going to say Ethereal Wireshark as well. And so basically the field numbers, protocol ID, version number, message type, flat and flukes. Then you've got route ID, route path cost, bridge ID, port ID, and so on. So then you've got the settings as well. So message age, max age, hello time, and forward delay. So basically the protocol ID is always going to be set to 0. Version number will be set to 0 with this one. Message type set to also set to 0 typically. And the flags, basically there's one for topology change, and so basically there's there's been a link that's gone down, and there's topology change acknowledgement as well. The route ID is of course the route ID of the bridge. Now, if they haven't done the election yet for the route bridge, they all assume that they are themselves the route until they learn otherwise. So the route path cost, of course, and so that will accumulate as further you go away from the route bridge. A bridge ID of the host that's the switch that sent it. Port ID, so what port number was it? Message age, the amount of time since the route bridge sent the configuration message. And then the max age is when the current configuration message will be deleted. And then hello time is time between route bridge messages. It's normally 2 seconds. And then there's a forwarding delay, which is the time the bridges should wait before any new state. So I think that's normally 20. So when a switch is powered on, it assumes it is the route bridge until BPDUs are sent from or received from other switches, and that may well have to change its decision there. So S3 compares its root ID with the root ID of the BPDU from S2, and S2 is lower, so S3 decides that S2 is the root bridge. But of course, once it's gotten one from the other switch, of course, S1 receives the information from S2, and because S1 has a lower bridge ID, it ignores the information from S2. S3 sends BPDUs out all ports, indicating S2 is the root bridge. S2 compares the info from S3, and so S2 still thinks it's the root bridge. S1 gets the same information from S3, that S2 is the root bridge, but because S1 has a lower bridge ID, it will ignore that as well. So eventually, once S1 has sent out BPDUs, all the other switches will go, okay, it's the root bridge. Now, S3 compares the info from S1, and now S3 sees now that the bridge ID of S1 is lower, and so it's the root bridge, and again for S2. Remember that after the root bridge has been determined, the other port roles can be determined because those roles are determined by the total path cost back to the root bridge. So we've had the election now. What happens next? Now, basically, back in the old days, the bridge ID was just 16 bits, and you plucked a number and you used it, and that was the way you went. But now, since VLANs have been available, they've actually put the VLAN ID in there. And so that's a 12-bit number, and it leaves 4 bits for the bridge priority. Of course, with 4 bits, you can count up to 16, so it still gives you enough options, I'd say. If priority is all set to the default, the lowest MAC address is the determining factor. The priority value can be modified to influence the root bridge elections. And so, again, of course, because the bridge ID, so the bridge priority is before the MAC address, it's the more significant number, and of course it will, of course, affect the elections. Okay, so there are different versions of STP. As you can see, there's quite a few. So there's 802.1d, that's the original from 1998. And then there's CST, then there's per VLAN spanning tree, which is Cisco proprietary. Now, Cisco does like its per VLAN spanning tree, and it can certainly have some advantages. It's got some disadvantages as well. So you will use more resources, but you can actually manipulate how different VLAN traffic moves, and you can sort of do load balancing. So there is some upside, definitely. So they actually updated the original standard in 2004, and then there's 802.1w, which is rapid spanning tree. And so it will often take ports 50 seconds to actually go from blocking to forwarding, and so these days computers boot a lot quicker than they used to, and so that can actually cause trouble with DHCP requests, and so they've had to speed things up. But of course, also faster convergence for rapid spanning spanning tree, of course, means that the network will be up a bigger percentage of the time as well. Now, Cisco, of course, after rapid spanning tree came out, they did their rapid per VLAN spanning tree. And there is also MSTP, so it's multiple VLANs with a single instance of spanning tree. So basically, this table compares them, and so of course, the two per VLAN ones are Cisco proprietary, the other ones are standards based. So resources needed, high and then very high for the Cisco one, but there are some payoffs in other traffic considerations. And the others go from low to medium to high. Convergence is, of course, faster with this rapid spanning tree. Now, per VLAN spanning tree. So original 802.1d defines a common spanning tree, one spanning tree instance for the switched network, no matter how many VLANs, and so you can't actually do load sharing. So one uplink must block for all VLANs. So it's less resources for the switches and a little less bandwidth used, but basically, if with per VLAN spanning tree, you can actually have a different route switch for the different VLANs. And so this would be a route port for VLAN 20, and this would be a route port for VLAN 10. And so the traffic would go different ways. And so you can actually, while you're gonna have one link shut down for each VLAN, it's going to be a different one. And so you're actually going to be using all your links. And so that is the upside of per VLAN. And so one port can be blocking for one VLAN and forwarding for the other, so you can load balance. So there is more resources used to run spanning tree, but it actually allows you to run more traffic across your network. So that's the reason why they bother going through that. Now, what port states can you have for a port? So blocking is basically before it started. And so basically the only thing that when blocking is basically it will receive and process BPDUs. That's all it will do. So if you've ever noticed when you plug a host into a switch port, it's got a yellow or orange light for some period of time and then it goes green. Well, that's actually STP spanning tree that slows down the port from coming up. And so it's actually going from those states from blocking through to forwarding. And once it hits forwarding, that's when the light is green. And so when it's in blocking mode, the only thing it will do is receive BPDUs and take a look at them. Now, with listening, again, we're still sort of in the process of learning who the route bridge is and who our route ports are and all that. Now, once it goes into learning, it will then look at data frames, and it will actually start filling its MAC address table before it actually starts forwarding frames. And so the beauty of that is it can actually sort of pre-fill its MAC address table, so it will need to do less flooding. And then once it cycles into forwarding, it will do every kind of frame. And so, of course, disabled just means nothing's going to happen. Now, as I said, the extended system ID field ensures each switch has a unique bridge ID for each VLAN. The VLAN number is added to the priority value. And then, so there, with example VLAN 2, the priority is 32770. So it's basically 32768 plus the VLAN number of 2. And so that's why it ends up like that. You can modify the priority number to influence the route bridge decision process. And there's several ways you can do it. Reasons to select a particular switch as a route bridge. The switch is positioned such that most traffic patterns flow towards that particular switch. Switch has more processing power and it's also easier to access and manage. Now, rapid per VLAN spanning tree speeds up the STP recalculations and converges quicker. And so, of course, per VLAN means it's Cisco proprietary. There are two new type ports, and so alternate port, which means it's disabled, and there's a backup port. And so you have an independent instance of RSTP running on each VLAN, and hence the per VLAN. Cisco features such as uplink fast and backbone fast are not compatible with switches that run RSTP. Now, so RSTP uses type 2, version 2 BPDUs, and of course remember the other ones were 0. A switch using RSTP can work with and communicate with a switch running the original 802.1d. BPDUs are used as keep alive mechanism. 3 missed BPDUs indicates lost connectivity. Edge ports. So basically you can configure a device as an edge port, which means it is an end device will be connected, never another switch. And so basically the command spanning tree port fast is how you do that. And so when you plug the cable in on one of those ports, it will go straight from blank to green. And that's good for a host. But if you plug the switch into there, there is no spanning tree running on that port, and so you could end up with a loop. So that's what you've got to watch. And so these are edge ports where you have a host plugged in, basically. Now, there are other link ports, so there's point-to-point. So it's a port in full duplex mode connecting from one switch to another switch or from a device to a switch. And then there's a shared port, which means it's running in half duplex mode and will connect to a hub. And so basically, with the point-to-point ones, if one of the cables fails, it can cycle back to an alternate port straight away. And so that's the upside of rapid spanning tree. With shared ports, basically, it has to behave like the old 802.1d. Okay, so how do we configure it? So, default configuration, you only have one VLAN, and so it is enabled. It's per VLAN spanning tree. It's not rapid per VLAN spanning tree. And so the switch priority, of course, is 32768, and the port priority is 128, and so the costs are 419 and 100 for the different port speeds that are available. Spanning tree port priority, 120 on everything, and so on. And so the hello time is 2 seconds between each hello packet that they keep track of one another. Forward delay time is 15 seconds, and then the maximum aging time is 20. So basically, 20 seconds of not getting a hello packet is what will actually trigger a new topology or a topology change, and then it goes from listening to learning for 15 seconds each, and so that's actually how it ends up being 50 seconds regularly. So, how do you configure a bridge ID? There's more than one way to do that, but as you can see here, there is spanning tree VLAN 1, root primary, and so basically that will have the lowest bridge ID, and so that will probably end up being the root bridge. If you have another port, that would be your second best one, another switch. You can actually do spanning tree VLAN 1 root secondary, and so that will have a slightly larger bridge ID. Oh, sorry, priority. Or you can actually just manually type in that number. But primary and secondary is a wonderful thing. Now, how do you figure out what's going on? Show spanning tree will tell you that. And so it tells you the root ID, and it will actually tell you if this bridge is the root or the root bridge is, and it will give you its. Now, port fast, as I said, that's what you would have to how you define an edge port. Puts a port straight into the forwarding state, and so of course that's allows DHCP to run quicker. Now, BPDU guard disables a port that has port fast from being configured on it as if a BPDU is received. So basically what we're saying here, we've got a host here, so that you should never be receiving a BPDU. So there are some attacks against spanning tree where you can actually have a host create BPDUs, and it can try to become the root bridge itself, and so then it will actually see a lot of the traffic. And so that's basically BPDU guard stops that. It will ignore all BPDUs received on that port. All right, so load balancing. And so basically, as we said, for VLAN 20, you could have one switch as the root bridge, and on VLAN 10, you would have another one as the root bridge. And so that will actually load balance traffic across the other trunk links. And so it allows you to use your redundant links more thoroughly. And so that's a wonderful idea. And so again, so you do root primary for one VLAN and root secondary for the other, and away you roll. And of course, you swap that over for the other switch that you want to do that. And so that's a great thing. And so it actually will come up with those values. Okay, so spanning tree mode, rapid per VLAN spanning tree supports RSTP on a per VLAN basis. And so it's not default though. So to turn on rapid per VLAN spanning tree, you do spanning tree mode rapid PVST, and that basically changes it. And so the spanning tree link type point-to-point command designates a particular point as a point-to-point link. So in other words, there's no hubs attached, or you can clear spanning tree detected protocols to clear STP. So how does it work? And how can we look into it? So you can analyze STP, and so you can discover the layer 2 topology. So show CDP neighbors will help you there. Prepare the expected layer 2 path, and so basically what would you think would be the topology, and then you would actually do show spanning tree for a VLAN to see what actually did happen and what paths are active and what ones have been disabled. Okay, so if the expected topology isn't the same as the actual topology, yes, that's when you might do a bit of investigation as to why it didn't work as you had planned. So either you didn't plan it correctly, or yeah, something else has gone astray. And so do show spanning tree and show spanning tree VLAN such and such to actually look into it. And it actually shows you which interfaces are doing what. And then if spanning tree fails or you turn it off, of course, that's when you can actually have your switching loops, and that is bad. Okay, so how do you repair a spanning tree problem? Basically, you would, or if you've got a broadcast storm, that's when you actually start unplugging cables. And so as soon as you stop the broadcast storm by killing the loops, you can then investigate what went wrong with the configuration to allow that to happen. Okay, switch stacking concepts. So you can connect up to 9 3750 switches together in a stack. One switch, the stack master, controls the operation of the stack. If this switch goes down, the new stack master is elected. It appears as one entity on the network, and so the stack is assigned one IP address, and so there's each switch has a unique stack number, and you can configure a priority value to determine which switch is the stack master. And the highest stack member priority value is the stack master. The stack master has the saved and running configuration files for the entire stack, and so there's only one config file to manage and maintain. Now, switch stacks. Basically, each stack appears as one spanning tree instance, and so it's treated as one switch. You can add switches without affecting the STP diameter. The maximum number of switches data must cross to connect between any two switches. And so basically, IEEE recommends a maximum diameter of 7 switches for default STP timers. And so basically from there, yeah, we've got 1, 2, 3, 4, 5, 6, 7, 8, 9 is your largest diameter. And so basically, if you stack them together, you've got 3 switches. Okay, so we're up to the chapter summary. So we looked at how to build a switch network redundant links, and we've looked at how different versions of the spanning tree operate, and we've looked at how to implement per VLAN and rapid per VLAN spanning tree in a switched LAN environment. So there's the logo, and so yes, we'll carry on from there. And so we'll have again some more advanced switching concepts coming in the next chapter. Have a nice day.